So
microinverter.
you learned about basically how to control the microinverter. And I'll talk a little bit about what we can do now with all of the smart inverters. So the regular inverter that you were talking about with Professor Ranade just takes DC and modulates DC to convert it into a pretty good sine, right? And you could do that with higher or lower efficiency. So that is kind of just the basic, just this minimum that you would ask from the inverter. Because fine, you take DC, you convert to AC. A lot of inverters that are for solar PV systems right now are not very smart. So sometimes you'll hear things like smart inverters. Does that ring a bell to anyone except for James? Maybe, well, and Anna. You guys, the two of you should know what a smart inverter is, right? So what can a smart inverter do? You have kind of a little bit of hints here. If you're gonna break it, then that much for your A plus.
It's pretty sealed, I suppose.
Yeah, it's sealed like from the potting as well. There may actually be a seal around it inside.
Oh yeah, it's not coming apart.
Oh,
Those
someone
three
has a
were just.
screwdriver. A flat. Oh, you have a flathead. Let's try to see if we can.
It's a cross.
Oh no, but
No, it was only for the.
Okay.
yeah, maybe if I could pry it open.
Do you want us to pry it open?
Yeah, it's broken already.
It's broken already. That's all we needed to hear.
Go for it. Okay, so while you guys are breaking stuff.
Yes.
So what you discussed is taking DC, converting it to AC, pretty good sign, quality sign, so that you have low THD, right? But now we have all of these requirements from inverters, and some of them are not microinverters, but they're large-scale, megawatt scale inverters that can do other things like voltage control. Sounds intuitive, right? Because you clamp the voltage on the outside, on the output stage. So obviously that will be AC RMS clamped operation. So voltage control sounds okay, something that you would already expect. But then there are things like frequency control, things like inertia, dynamic grid support, fault write-throughs. So those are all the interesting things that you get now from smart inverters. And so I have my yes we can, because a lot of times people will say, oh, inverters cannot do that. So this is where I will ask you guys, if I want to change the voltage amplitude, RMS value of the output of the AC stage with an inverter, can I do that?
Yes. Amplitude modulation.
Up to what?
Amplitude modulation.
Amplitude modulation. So that's already a simple thing to do, and it's not something that we should be surprised about. How about frequency control? Can I change my frequency from 60 hertz to 61 hertz, the upper stage? From DC to 61 hertz. So am I required to have 60 hertz?
Yes.
Yes, by utility regulation. But can our power electronics do that? Can you modulate your switches to get 61 hertz, 59 hertz,
Yes.
50 hertz?
Yes.
Yes, we can. So that's frequency control or frequency support of the grid operations. And then there are other things like inertia for grid operations, for power systems operations. So everybody have taken power systems class? Yes? If I say system needs more inertia, what would I mean by that? We need more inertia for stability.
The changes should be slow.
Changes of what?
Change in the load requirement. I mean,
Load
the
requirement leads
rotating
to
machines,
what?
they provide the inertia.
So when you say inertia, is it inertia of load as in kilowatts, megawatts, reactive power, kWars, mWars. What do we mean when we say we need more inertia? We're looking at mostly power people. You guys are in micro, right? So power people. And they say, I need more inertia. Or the system has high inertia, or the system has low inertia.
I don't know. I would think more frequency related because I know it was what he was saying about like the torque of the motors, and then like you don't want it to spin too fast.
Right, so what would I want to change? Faster or slower frequency? Or
The speed of the
Speed.
rotating machine,
which leads to what? Which generates what?
more frequency.
Frequency, right? So if your system is, if your frequency is drifting between 60.005 and 59.09995, that's basically your rate of change of frequency, right? So a lot of times, this is a detour for you guys who are not power system people. In power systems, people came up with term rate of change of frequency. You heard that?
Mm-hmm.
And so it's basically nothing but DFT, right? So whoever came up with that term means they had no control buses, which is interesting. Okay, so what are we asking inverters to do? And so when we say smart inverter functions, that just means that we are asking an inverter to do something that is not a traditional taking DC, converting to a fixed output clamped voltage operation of a given frequency. So we're asking to do something different, different frequency, different output voltage, or other couple of things is where we will start thinking about reactive power production from the inverter or reactive power generation out of inverter, so the same as production. So a lot of times the remote on-off is kind of simple thing, right? You just TCP IP into it. But power factor control, that's where, oh, you guys don't see my mouse. So power factor normally in an inverter is designed to take DC power and convert that with the highest efficiency to AC. And so normally that highest efficiency would mean power factor of what value? 1. So a lot of inverters, until pretty much now, inverter had one job in life, to take DC, convert the DC to AC power of ANSI range power factor 1. And ANSI range means something to a couple of people. Do you want to explain to them what ANSI range is?
ANSI range?
Yes.
0.8 to, will that ring?
James should know that. What is ANSI range?
Would you refresh me?
What she said, what he said? The range where your ants, can we, this is my ant picture. It's a range that's applicable to ants?
No.
No.
Like, no, not at all. But
Okay, it's the last class of the semester. Everything's all over the place. So ANSI range is American National Standard System. So that tells you that your voltage, RMS voltage of the system should be between 105 and 0.95 per unit values.
it stood for American National System what?
National
Standard
System.
system, so SI, International Standard. But basically that just tells you that your acceptable voltage is between these limits. There are some emergency ratings, but as you just convinced me, we can generate power output that goes into our AC system that could be variable amplitude, right? So we can have 107 here, we can have 1.1, we can have 0.8. So want, so I'm still on point number 2, power factor. Previously, all of the inverters had one job in life, to take DC power, convert it to AC, regulated AC voltage on that ANSI range between those voltage levels, and of a fixed frequency. So 60 Hertz for North American, 50 Hertz for Europe and other countries. And so that normally would translate into power factor of exactly 1. And so for power system people, you guys know that reactive power is important, right? So sometimes you need power factor that is not 1. You may need, I don't know, leading lagging power factor, 0.7, 0.8. You may need reactive power control or reactive power compensation. So that means we should ask our inverter to provide power factor that is not 1, but some other number. So that is called power factor control. Can you guys produce power factor that is not equal to 1 out of this?
Not the one?
That is not equal to 1.
Yes.
Yes, we can. What would you do for that?
What's the application for that?
No, how would you produce power factor that is not equal to 1?
I guess make it produce a lot of reactive power.
Yes, but how?
Oh.
Control the amount of power which is produced from it, like, because it is the ratio of the real power to the apparent power. So that 2 wave shapes within one other.
Yes, so basically you want to delay your current or voltage waveforms relative to each other, right? So to produce leading or lagging, delay current or delay voltage. And how did we do those delays? The capacitor, firing angle, or pulse width modulation that is shifted in current or voltage. So basically, yes, we can, right? We can provide power factor that is not equal to 1. Okay, then I also have volt var and volt watt functions. Does this mean anything to anyone? Should mean something to Anand.
The reactive compensation,
Reactive compensation. So what's the difference between volt var and volt watt?
the reactive, the active power.
And-
By changing the phase angle, the active power can be changed. And
Yes.
changing the magnitude of the voltage, the reactive power can be changed.
Yes. So let's look at a couple of those slides. So this is where people who are in power systems, this should be like a Bible, especially for Anand and James. So you'll have, here's my mouse. Did you guys open it?
Not yet. Kind of working with the understated tools.
Right. Does anyone have a knife or like give it a try?
You're not allowed to have knives on university properties.
Not even
That was
pocket
a
knives?
trick question. So the correct answer should be no.
I'm just kidding, y'all. Unless you really have it.
All right, so this is how we describe smart functions in the inverter. I feel like, let me take one step back. Let me tell you what James is doing for a project, and then we'll think about what we need to do. Okay, so if we have a large PV system, like this scale, so this could be, I don't know, a megawatt, half a megawatt, couple of megawatt PV installation.
Ooh, that's a lot.
That's a lot.
It's a sexy picture.
That's a sexy picture. Do you guys see any inverters here?
Inverters?
Yes.
No.
Where are they?
Underneath.
Probably away. Not like. I wouldn't say underneath. Probably like they have a big old box somewhere like away.
So why would you hide it?
Why would we hide the inverter?
Why would they hide it?
Keep it out of the sun.
Well, just because you wouldn't want an inverter for every single panel, that'd be ridiculous. Like it would probably be like one huge central inverter.
Home installations, they do
What are
like.
you opening right now? You said having an inverter per each panel would be ridiculous.
Oh, these are optimizers?
Well, no, you guys just had that microinverter, so that
Micro-
inverter is one per panel, right?
Uh-huh.
Right.
So that's not ridiculous.
Well, on the house scale, but like maybe on something that big, to have one inverter for every panel would be, I don't know, I guess it's possible.
So, define ridiculous.
Maybe not, well, because like, that's a lot of maintenance, like on every single one of those, and if you just have one central one, then you just only have to worry about that one.
Even on a home install, you have one of those per panel.
Now, you could also have a central inverter, what we call
Right.
like Solar Edge, and like, those ones are probably rated at like 230 watts.
So
A
that's
central
still a
inverter,
microinverter.
a central or a micro inverter, whatever, like, you could have them as big as like 5,000 watts.
So what's micro about it?
Micro?
Who are in micro track, micro means what?
Small.
That's way huge than your power systems, right? So is that micro or is that not exactly micro? Where would that open one is?
Changes, micro changes in the,
You could have micro and string, I should say. Micro and string inverter.
Yes, so string means you basically take Christmas lights arrangement of PV panels, so it's a string, electrical string. And then you add voltage from all of the PV panels, and then you invert that together. So microinverters take indeed just one PV panel, so one DC input. So you have one DC input, one AC output. And so that's normally single phase or split phase. So micro is a relative term, right? It's just micro because it's micro relative to a megawatt scale. So it's micro because it's not that big. So for a couple of PV plants, I think I may have these two. So James was right. We actually can believe him sometimes.
Poor James.
And he has to do research with me, so. So normally he's right. Larger scale inverters, well, whatever that is, this is artist's drawing. You will have an inverter that will be co-located with a transformer that might also be co-located with a substation. Actually, let me show you a better picture. No. So,
Get a hammer if you can.
you guys can stop already. So actually, what does this tell us? This tells us that, well, first of all, your professor is easily distracted. And the second part is when inverter manufacturers or optimized manufacturers do all this plotting, this is really, really made so that you can't open it, so that this, any of the screws will not come loose, and even if they don't come loose, even if they do come loose, you will still have some mechanical integrity from the gooey, gluey stuff. So you're demonstrating the purpose that it served the purpose. Okay, so transformers and inverters for large solar applications may now look like this. It's basically like a shipping container that will have inverter on this side and then step up transformer right there in the same shipping container. It looks something like this. So this is not a very high definition picture.
You're gonna cut it and then prep from where you cut it.
Yeah, so you'll have a solar inverter, transformer, and then you'll have any of the other controls. So that's basically how large-scale inverters look like right now. But if we look at the previous picture that I didn't like specifically, so that's the inverter side of that same inverter/transformer combination. So what could you guys, can you guys recognize any of those components here? I mean, I know this is kind of low res and I have a better picture, but today is just a mess. Anything that looks recognizable?
Is this the transformer or the inverter?
Well, you tell me. That's why I'm asking you. Can you can you see?
I guess it maybe looks like windings right there. I don't know if that's resolution or poor
So
resolution.
here's a cutaway that shows inverter on this side, this Homer kind of in the center. I think I may have a better picture, but hold on, let me unplug. I'll show you later, since that's kind of your work. I'll show you later. But Anand, any suggestions on what those could be? Or those could be?
I think I need some glass.
Would you like to borrow mine?
So some of those could be, I don't know exactly where the fuses are, but you'll have multiple input fuses, and those are those cylinders because those are fuses for like 50 amps, 20 amps, 50 amps, 70 amps, 100 amps fuses. And so you'll have many, many, many fuses, input fuses. Why would you need so many of them? For a large PV installation?
Well, because if one of them goes out, you don't want the whole array to go away.
So how many inputs are here?
I don't know. A lot.
A lot.
More the better, probably, but you know.
One per each panel?
No.
How many per?
Probably they probably go by string, like maybe like 100 or maybe 1,000 per string. I don't
Okay,
know.
so we're on the right track. This is where I wanted you to open. Oh, come on, James, we need your SAM.
My login.
No.
Oh, I have my laptop.
Today's class is just not working.
I can log in.
Well, can you log in on my computer or is it per email? It's
Per email, and then the key. I don't know. Is it just your random code?
Okay. Things are not working out today. Let's
What
think
is
about-
SAM supposed to be?
You want me to show everybody?
Sure.
Sweet. Except I don't know if mine has an mine doesn't have an HDMI. What is that?
It's an HDMI. Yeah, it's an HDMI. Everything here is HDMI. That's why Professor Ford didn't work.
Yeah, I don't have HDMI. I could just find my code real quick so we could log in.
Alright, let me show you what Alex is opening up.
That'd be nice.
And then, okay, so let's think about PV streams. So if you have this PV array, which is one long string, electrical string, and if you're talking about, for example, residential PV installation with things like rooftop, if you have things like a chimney that will may provide shading sometimes, this kind of chimney, or if you have any other structures on the rooftop that may cast a shadow here, then what might happen to your electrical string of a PV system? If you're basically providing that electrical connection as a Christmas lights arrangement, so each PV panel will have its voltage and current. So if you cast a shadow on one, then what happens to voltage and current of one PV panel?
It affects the rest unless some optimizers are there.
But so how does it affect it?
Through the current, right? So if it's a string, like say this one's not getting as much voltage or power or whatever, producing as much, then it'll transfer. Say it's someone getting half power because of the shade, it'll only transfer half the amount of current it's supposed to the next one, and so that next one, even if that one's doing full power, it only has, I don't know how to explain this.
Any better explanations? Any better explanations?
I guess like like when you have Christmas tree lights, once you take out one, the rest get affected, and then so like if one's loose, then all of the rest are gonna be a little dim.
It depends on the configuration.
It is going to affect the output only of that sound.
So, PV panel produces current and voltage, right?
kind of equivalent model can we use
for PV panel?
for a PV panel?
Is it voltage source, is it current source?
Current, so.
Okay, so we will have several current sources in one screen location. If one of those goes out, or is completely broken, or just doesn't have enough light to produce enough current, then what happens here, in terms of my output,
The total output current is less than what it should be
right, and by how much?
by 1 out of whatever, 1 out of X, I should say.
So if this is current source, how would I draw my current source representation?
What's the X-axis? Voltage? Oh, sorry.
Current is high, the voltage is,
So current does not do what?
no, current is high.
Current is high. Does it change with voltage? It's a current source?
No,
No, so our current source is normally just fixed current independent of voltage. So if we have current source one, current source, I don't know, 5, this is I1. Suppose my I2 is terrible, I don't know, noise level. What will happen to my output, my total current? Between all of those current sources. So suppose I1, 2, 5, actually 3, 4, 5 are all high, and I2 is terrible. Maybe not completely open, but just real low. What do I get here?
A lower line.
Lower, which is equal to,
slightly below I.
it's going to be current limited by your weakest link, right?
Oh,
Weakest
really?
link, right?
Yes, yes, actually. Yes.
Alright, so.
That's why we have optimizers.
Right, so here we'll get minimum or pretty close to minimum of all of them, right? So, if I have one of those boxes that Alex is still torturing.
I got it. Don't you worry about this.
What can we do to one of the weakest links to boost the current?
You said it boosts
Yes, so what do we need to boost, voltage or current?
current.
Yes, so we need to boost current to the same, or at least the same average of all of the rest. So what do we need to do to voltage? For boosting current?
Lower voltage?
Right, so normally, each of those PV panels will have their own voltage drop, right? So our goal is to match current to the screen current, and therefore we can sacrifice a little bit of voltage. So that's what those guys do. Alright, this was a long detour. So, how many of those do we need per each of our PV systems?
Ideally 1 per panel.
Ideally 1 per panel. Is that going to be ridiculous, like James said?
Well, on a residential, no. But, well, actually, I don't know. on a large scale, maybe not 1 per panel, but maybe 1 for every few sets of strings or something.
What do you think? 1 per panel, 1 per string, 1 per 3, 5, 10?
Because I'm just thinking like cost and maintenance. There's like 1 for every single panel. Like there could be 1,000 panels, and then like you have to do maintenance on every single optimizer.
Well, that depends what kind of maintenance do you want to do. Do you want to go up on the roof and do something like what Alex has been doing for the last half an hour?
No.
Do they even require maintenance?
It's what?
Do they even require maintenance?
No, so that's exactly what I was saying, that normally you don't want to do any maintenance. You may want to be able to communicate with it, either TCP/IP or power line communication, but you don't want any maintenance. So some of those things, basically you put them in parallel.
You should buy more of these, cause they're really well made.
Where are,
Just saying.
let's watch a video. Supposedly they can videos.
Your turn.
You are almost there.
So close.
If it were up to me, I would've gone to the
We
basement to
don't
get
have
the drill.
sound here.
Oh, sure would have been perfect.
No sound. That's what happened when Professor Allen changes everything. Okay, so this was a prime example of, not even as bad as just a chimney shadow, but any irregular leaves, bird poop,
Fun.
whatever, can basically reduce your string output if a bird poops strategically.
That sounds like something that would happen.
That does happen all the time. Happens all the time. So then basically you can lose the whole string output because of one bird strategic poop. So you basically have one of those per each microinverter. So you'll have DC input from each PV panel that will go into what James is breaking. And then
Trying to.
boosted DC output will go in microinverters. So there you go. You guys get an animation here. You can have different model numbers that do different things. You guys confused yet? And still no show and tell? So close?
I could see green on the circuit.
All right,
Oh my
well,
God. And there's more screws in here.
I think I can let you guys go today because that's just, today's class was not optimized. There, you can get an animation showing the current limited. This is like current explanation for non-electrical engineers, right? And it's an interesting analogy, but I think I'm gonna let you guys go because this was not an optimized class. Did Professor Andy promise you a final assignment or
No, just a homework.
just homework? And he has homework, right?
Mm-hmm.
Okay.
He has homework, you have the discussion,
Right.
and Dr. Firth also has a homework for
Okay,
next
so
week.
you guys are busy.
Yes.
All right, good. Okay, well then, go.
Wait, is Firth coming to teach?
Right now?
Today.
No.
No, he's done.
Okay.
I didn't know if Ronald was joking or like. You want to take this to Carl Lab
Yeah.
and hammer it out?
I wanna,
But we don't have a class next week, right?
No, because, well, Professor Brandon and myself are traveling, so.
Does this
Okay.
mean final class of the semester?
Yes.
Oh, now you decided. Yes, this is your final class of the semester. If you guys want to learn more about